Hi all, welcome back to the another session on quantum mechanics. So today we'll continue the Schrodinger picture. So in the last lecture also we have discussed the Schrodinger picture. We have just introduced the Schrodinger picture, and I think it is good to just revise what we have learned in the last class. Okay, so we know that according to the postulates of quantum mechanics, the output of any measurement is just expectation value of the given operator, and it can change with time. Okay, so there are different ways for the evolution of the system, or the evolution of the expectation value of the operator. So one of this picture is called Schrodinger picture, so in which only the state of the system evolves with time, the changes with time, and the operator was completely independent on time. So if that is the case, then we can connect the state of the system at some time t0 to the state at the time t through a linear operator. The linear operator I defined as I will just represent it as utt0. Okay, now this linear operator, we can show that this linear operator follows the property of unitary operator. Okay, so we can show that this u is the linear operator is nothing but a unitary operator, such that u dagger and u dagger u is identity. So this we have already proved in the last class. Okay, now since u is unitary, it is possible to represent that unitary operator in terms of a generator. So the infinitesimal unitary transformation, that is the unitary operator connecting the state at t minus delta t to the state t. So this is a small time evolution, delta t time evolution. So it is called infinitesimal unitary transformation. So the unitary operator corresponding to this infinitesimal time evolution can be represented in this way: the identity operator minus I by h cross the h of t delta t. This h of t is called generator, and this generator is nothing but the Hamiltonian. Okay, now since the infinitesimal unitary transformation follows the this representation, we can show that the time evolution of the unitary operator has to satisfy this first order differential equation. So IH cross dou u by dou t is h of t u t t t0, where h is the Hamiltonian of the system, and we already know how to find the Hamiltonian. We have to just replace the classical Hamiltonian with the quantum mechanical operator. Okay, so since this is the time evolution satisfied by the unitary operator, we can find out what is the time evolution satisfied by the state vector, and we can show that IH cross dou psi by dou t, where psi is a function of time. Okay, so if you want, we can just keep a t inside. So IH cross dou psi of t by dou t is h of t psi of t. So this is called the time independent Schrodinger equation. So once you solve this equation, we will find out what is the state of the system as a function of time. Then we can find out the expectation value of operator as a function of time. Okay, so we can just see what would be the time evolution of the expectation value using this Schrodinger picture. So we can find out what is the first derivative of the expectation value of the operator. So according to the definition of the expectation value, it is psi si. So in Schrodinger picture, only psi evolves with time. So this is equal to d psi by dt asi. So we have to use the product rule. Then psi a d psi by dt. Okay. Now d psi by dt can be written as minus I by h cross h of t psi of t. Then what would be broad d psi by dt? That would be plus I by h cross psi of t h. Okay, so therefore this first expression we can write as I by h cross psi h a psi plus psi. So d psi by dt can be written as minus I by h cross psi a h psi, or this can also be written as 1 by I h cross psi a h minus h a psi. Okay, so if this I, if you go to denominator, it will become minus. So this can be written as minus 1 by I h cross. This can be written as plus 1 by I h cross. Okay, so 1 by h cross can be taken as common. So it becomes inner product psi a h psi minus inner product psi h a psi. So that can be written as inner product psi a h minus h a psi. So this is equal to 1 by I h cross psi ah minus ha is nothing but commutator ah psi. So what is the left side is the time derivative of the expectation value of the operator. Okay, so therefore the time derivative of the expectation value of the operator is 1 by I h cross. Now this is nothing but the expectation value of commutator ah. Okay, so now we have got the expression for the time evolution of the expectation value. Now this can be treated as the equation of motion. Okay, so this is the equation of motion in Schrodinger picture. The time evolution or the time derivative of the expectation value of the operator, the time evolution of the expectation value of the operator has to satisfy this condition. Now it is very easy to show that if any operator commutes with the Hamiltonian, then its time derivative would be 0. Okay, so if better we can use blue color. So if the commutator AH equal to 0, then the d by dt of expectation value would be 0. That is, the expectation value of the operator would be constant if that operator commutes with the Hamiltonian. So such type of the quantity are called the conserved quantities. Okay, the quantity which are the constant in time, they are called conserved quantities. Okay, so an operator or the output of any measurement would be constant in time if it commutes with the Hamiltonian. So this gives the idea about the conservation quantities. Okay, so the conservation quantities, the operator corresponding to conservation quantities has to commutes with the Hamilton. That is the simple condition we can say. So these details, the very detailed discussion about the conservation, you will learn in another chapter. So that is why I'm not discussing here. Okay. Now the other part of thing is what about the stationary state? So we can define the stationary state in quantum mechanics or in Schrodinger picture. Okay, so let get phi I are the eigenvectors of the Hamiltonian with eigenvalue EI. So that is the Hamiltonian acting on ket phi I can be written as EI ket phi I. Okay, so this ket phi I, okay, I'm not giving any time dependence on this. Okay, H acting on ket phi I is EI phi I, ket phi I. Now the corresponding the state vector we can define this way. Okay, suppose this the state of the system at time 0 is ket phi I. Okay, so better I can denote that by symbol psi I. So psi I of 0 is ket phi I. Then what would be the psi I at some later time t? Okay, so this is one question. So how would be the time evolution for the energy eigenstate? This ket phi I is a Hamiltonian of the eigenstate of the Hamiltonian. So this is nothing but energy eigenstate. Okay, so this we can find out. So for that, what we can start is the starting point is the expectation, the time evolution of the unitary operator. The IH cross du by dt is known to be HU. Okay, suppose if the Hamiltonian is not a function of time, then du by u can be written as 1 by or minus I by h cross h into dt. So if you integrate it, ut t0, we can get it is exponential of minus I by h cross h t minus t0. So or u t comma 0 is given as e raised to minus I by h cross h times t. Okay, so this is the explicit representation of the unitary operator if h is not a function of time. Okay, so then what we have discussed is we have just represented the state, initial state as ket phi I. Then what would be the state after some time t? So the psi I of t can be written as u t 0 psi I at time 0. Okay, so what is ut0? It is e raised to minus I by h cross h times t. And what is psi I of 0? It is nothing but ket phi I. Okay, so e raised to minus I by h cross h t acting on ket phi I. So e raised to minus I by h cross I can write as 1 minus I by h cross h t plus minus I by h cross square by 2 factorial h square t square plus etc. acting on ket phi I. So this would give 1 acting on okay, this is something but identity operator. Identity operator acting on ket phi I would give ket phi I minus h acting on ket phi I would give ei ket phi I. So this can be written as minus I by h cross eit, then minus I by h cross square by 2 factorial h square acting on ket phi I would give ei square t square plus etc. acting on ket phi I. So this is nothing but e raised to minus I by h cross eit ket phi I. or e raised to minus I by h cross EIT psi I at 0. So psi I at time t is e raised to minus I by h cross EIT psi I of 0. So that is the state at time 0 and state at time t differs only with the phase factor. So this we can call it as a phase factor, or more correctly it is called as a dynamical phase. Okay, we can show that there is no relevance of this phase factor once you are finding the expectation value of the operator. Okay, so we can find out what is the expectation value of operator at a time with the state psi I of 0. So this can be written as psi I of 0, the operator A, psi I of 0. Now what would be the expectation value of operator at later time, which is psi I of t? So this becomes psi I of t, the operator A, psi I of t, which is equal to the ket psi I is e raised to minus I by h cross EIT ket psi I of 0. Therefore, the bra psi I of t would be the bra psi I of 0, then e raised to plus I by h cross EIT, then operator A, then ket psi I of t is e raised to minus I by h cross EIT psi I of 0. Now this is just numbers. Okay, so remember EI is just energy eigenvalue, it is not an operator. So the number always commutes with the operator. So we can take this to the left side and then they will cancel. So e raised to plus I by h cross EIT and e raised to minus I by h cross EIT would cancel each other. So therefore the result would be the psi I of 0 A psi I of 0. So that is nothing but the expectation value of operator A times 0. Okay, so what its meaning? So expectation value of operator A at the time t at time 0 are same if the state is stationary state. Okay, so recall the psi I of 0 is taken to be ket phi I, where ket phi I is the energy eigenstate, or it is called the stationary state. Why it is called stationary? Because we have shown that there is no time evolution for the expectation value of the operator if the system is in the energy eigenstate. Okay, so if the initial state is the energy eigenstate, then the expectation value of the operator remains constant. That is, the expectation value of the operator at time t is same as the expectation value of the operator at a time 0 if initial state is energy eigenstate. So therefore the energy eigenstate is called stationary states. Okay, so now you can ask the question again. So why the energy eigenstate is called stationary state? So there are two reasons for it. So the first one is if the initial state is the one of the energy eigenstate, then the system will remain in that state. Okay, so here what we have shown here, the psi I of 0. So if psi I of 0 is get phi I, so that is if the initial state is one of the energy eigenstate, then at later time also the system remains in the same state apart from a phase factor, apart from a dynamical phase. Okay. So if initial state of the system, we can represent it as psi of 0 is one of the eigenstate is in one of the energy eigenstate, then the system remains in that state. Apart from an additional dynamical factor, dynamical phase factor. Okay, so if psi of 0 is one of the energy eigenstate, so better I choose psi I, because to represent, because there are different energy eigenstates possible. The first energy state, second energy state, and so on. So that is why I just introduced a subscript I. So if psi I of 0 is get phi I, then the later time, the state of the system would be in the same state, psi I of 0, but there would be an additional phase factor e raised to minus I ei t upon h cross. So there is no mixing up of state in the time evolution if the initial state is the energy eigenstate. So there is a one reason that that is the energy eigenstate is said to be the stationary state. And the second thing is the expectation value of operator, or the time derivative of the expectation value of operator, is 0 if the state is in the one of the energy eigenstate. So the expectation value of the operator is constant in stationary state. So these are the two reasons why the energy eigenstate are said to be the stationary states. Okay, so so with this, we have completed our discussion about the Schrodinger picture. Okay. Now I want to take attention to the comparison between the classical mechanics and the quantum mechanics formalisms. So in classical mechanics, you have heard about the Poisson bracket formalism. So in Poisson bracket formalism, we can write the Hamilton's equations as the Q dot as the Poisson bracket QH and P dot as the Poisson bracket PH. So in general, the time derivative of any dynamical variable dA by dt is commutator, sorry, not commutator, the Poisson bracket AH. Now, when you're going to the quantum mechanics, then the dynamical variable, the observed quantities are not directly the dynamical variable. They are the expectation value of the operators So in quantum mechanics, in general, the time derivative of the expectation value of the operator is given by the 1 by IH cross. Okay, so or the expectation value of 1 by IH cross the commutator AH. So if you compare these two equations, we can see that there is a direct analogy between the Poisson bracket and the commutators. That is the Poisson bracket AH in classical mechanics will be replaced by 1 by IH cross the commutator AH in quantum mechanics. Okay, so you can see this kind of the connection from classical to quantum or the quantum to classical. Okay. Then, so this is the Poisson bracket formalism for classical mechanics, and in quantum mechanics, this is a general expression. Okay, now here Q and P are, yeah, you can take this Q and P are generalized coordinates and generalized momenta. So one of the possible generalized coordinate and generalized momentums are the positions and momentum. Then if the Q is X and P is the momentum operator, then in quantum mechanics, we can guess it should be d by dt of the expectation value of position operator. That would be nothing but 1 by IH cross the expectation value of 1 by IH cross the commutator XH and d by dt of the expectation value of momentum operator would be 1 by IH cross the commutator PH. Now in classical mechanics, this Q dot it is possible to show that this Q dot is nothing but P by M, and P dot is minus dV by dx. Then can you show this is equal to the expectation value of momentum operator by mass, and this is the expectation value of minus dV by dx. Okay, so this can be done as assignment. So prove that the d by dt of the expectation value of x is the expectation value of momentum by mass, and d by dt of expectation value of momentum is nothing but minus dv by dx. Okay, so now the one main point I want to make is we can always compare. It is possible to, in most of the cases, you can compare from classical mechanics to the quantum mechanical systems. Okay, so that is the expectation value of the operator obeys the same equation of motion in quantum mechanics as the dynamical variables in classical mechanics. So this is called the Ehrenfest theorem. Expectation value of operators in quantum mechanics obey the same equation of motion as the dynamical variables in classical mechanics. Okay, so the in classical mechanics we know that dx by dt is nothing but p by m. So this is the equation of motion in classical mechanics. So when you are going from classical mechanics to quantum mechanics, you have to replace the dynamical variable with the expectation value of the corresponding operators. Okay, because the dynamical variable is not directly an observable quantity in quantum mechanics. So that is what is called the Reinfeld's theorem, that the expectation value of operators in quantum mechanics obeys the same equation of motion as the dynamical variables in classical mechanics. Okay, so this can be taken as the illustration of the Reinfeld's theorem. Okay, so you try to do it as an assignment. Okay, if you are not getting, then we can discuss in the live session. Okay, so with this, we have completed our discussion about the Schrodinger picture. So we can just summarize what we have discussed so far. Okay, so in Schrodinger picture, the state at time t connected to the state at time 0 through a unitary operator, and this unitary operator will satisfy the differential equation h cross du by dt is HUTT0, and therefore we will get the corresponding the time dependence equation for the state vector, which is IH cross d psi by dt is H psi of t, and this is what is called the Schrodinger equation. Okay, now using the Schrodinger equation, we can find what is the time evolution for the expectation value of any operator. The time evolution for the expectation value of operator is given by the expectation value of 1 by IH cross, sorry, the commutator A comma H. Okay, so if an operator commutes with the Hamiltonian, then the corresponding operator or the corresponding dynamical variable would be a conserved quantity. So that is a result from this thing. Okay, and finally, okay, then later we have introduced what is called the stationary state. So stationary states are nothing but energy eigenstates, is H phi I is AI phi I. Okay, and we saw that if the system is already in the energy eigenstate or in the stationary state, it will remain in the state forever. Okay, so if psi I of 0 is get phi I, then the state at later time would be e raised to minus I EIT by H cross psi I of 0 or e raised to minus EIT by H cross get phi I. So if the initial state is one of the energy eigenstate, then at the later time also the state of the system will remain in the same energy eigenstate, but apart from a phase factor. So this is called dynamical phase, and there is no relevance for this dynamical phase usually. The thing is, if you find the expectation value of operator, or if you find the norm of the vector, the dynamical phase cancels. So that we have shown earlier, that is expectation value of the operator at time t and the expectation value of operator at time 0 would be same if psi I of 0 is get phi I. So if the initial state is the energy eigenstate, then the expectation value of operator would remain same, or the time derivative of the expectation value of operator would remain 0. So that is what is called the stationary state. And you might have heard about this stationary state in Bohr model, which is the semi-classical model. So in which we assumed the electron will revolve around only in this, or the electron will remain only in the stationary orbits of the atom. So where we have defined the stationary orbits having angular momenta as multiples of h cross. Okay, so that is called the Bohr's the postulate. Okay, so that is what is called stationary state. And finally, we have discussed the Ehrenfest theorem. So Ehrenfest theorem states that the equation of motion of classical dynamical variable and the quantum mechanical expectation value will follow the same structure. Okay, so we have to just replace the classical dynamical variable with the corresponding the quantum mechanical the expectation value of the operator in order to get the equation of motion. Okay, so that is what is called the Ehrenfest theorem. And so with this, we have completed our discussion about the Schrodinger picture. So the main takeaway is this equation. So this is called the equation of motion for the expectation value of the operator, because that is the what is the observable quantity. Okay, the state is not observable, only the output of the measurement is what is called the observable. Okay, so with this we can stop Schrodinger picture. So in the next class, we'll be going to discuss about the Heisenberg picture. So thank you for watching this video. We'll see you in the next class.